we're going to rigorously prove the following statement in the theory of sequences, that a convergent sequence xk of points in Rn, n-dimensional Euclidean space, is bounded. Now intuitively this makes sense. If you have a sequence that's approaching something, then it can't go off to infinity. But we're going to be very precise and rigorous in our proof to really practice with mathematical proofs and introductory real analysis to give you the confidence you need to master the rest of real analysis really. So let's first talk about what these two terms mean, bounded and convergent sequence, and I hope this really gives you a lot of intuition about these concepts. So bounded basically means that you can sort of choose an m. Okay, so bounded means the following. I'm going to write it as follows. Bounded means that there exists an m. So we can say there exists a number m such that the norm of xk is going to be less than or equal to m for all k. Okay, so for all terms in the sequence, the norm of xk is going to be less than or equal to m. You can think of the norm, if you like, as the distance from xk to the origin inside Euclidean n space. So that distance is going to be less than or equal to m for all k. So another way of looking at it visually is if you sort of imagine, here's the plane, you have a ball of radius m containing the origin. Okay, so its radius is going to be m, and all the terms in the sequence are going to be in that ball. Okay, so all the terms in the sequence are going to be in that ball. That ball could be really big. It doesn't matter how big m is, but there is some m, so all the terms in the sequence are in that ball. And convergent, what does convergent mean? Well, convergent means, the formal definition of convergence means that if you take your limit, okay, so we say that xk is going to converge to x, okay, that's our definition we're looking for. It means that if you take our limit x and we choose whatever small ball containing x that you like, okay, so small ball is all the points inside n-dimensional space that are within epsilon of x, within a radius of epsilon of x. X is the center of the ball, so you can write this as b of x epsilon. It's going to be all y inside Rn, such that the distance from y to x is going to be less than epsilon. Okay, that's going to be your epsilon ball, centered at x, radius epsilon, and no matter how small you choose that ball, the terms of the sequence are eventually going to be in there. Okay, so eventually means that for some sufficiently large term of the sequence, beyond that it's going to be in the ball. Okay, so we can say that there exists a big K such that for k, little k greater than or equal to big K, we can say that the kth term in the sequence is going to be inside this ball, b of x epsilon. So its distance to x is going to be less than epsilon, no matter how small epsilon we choose. So it may be very large, okay, it could be the first billion terms, trillion terms outside the ball, but as long as eventually they're in the ball, that's all that matters, and that's going to be crucial to our proof. Okay, so what we're going to do is we're going to prove that a convergent sequence is bounded, so we need to find a bound for all the terms in the sequence. So how are we going to do this? Well, we know that eventually the terms of the sequence are going to be in the ball, and the ball itself is bounded, right? It doesn't matter how big x is. X is going to be somewhere, and then you take this little ball containing x. It doesn't matter what radius we pick. Let's pick epsilon as 1. That's also going to be within some large number of the origin. Okay, so all the terms eventually are going to be bounded. So let's make that precise, and then let's give a bound for all the terms in the sequence. So I'm going to do that right here. All right, so we know that, so we pick epsilon equals 1, use the epsilon n definition of convergence with epsilon is 1. So pick epsilon equals 1 and choose a k. So it doesn't matter what k we choose. We can choose a k, okay, because the limit of xk is going to be equal to x. So choose a k such that the distance from x to xk is going to be less than 1 for all k greater than or equal to k. Okay, for all little k greater than or equal to big K, you're going to have that distance. Now we can bound the terms xk. Okay, so we know x is some distance from 0. Okay, we know that. And what we can do is then we can say that the distance from xk to 0 by the triangle inequality, it doesn't matter. Suppose our x is here and we have this ball like this. We can approximate our distance to 0. We can upper bound it by saying that we first go to x. So we say this is xk. And then we go to x, which is our limit, and then x to 0. So that's a triangle inequality that then says the distance from xk to 0, or in other words, the norm of xk, which is what we're trying to bound, for little k greater than or equal to big K, is going to be less than or equal to the distance from xk to x plus the distance from x to 0. Okay, which is just going to be less than 1 plus the norm of x. Okay, so whatever that is, norm of x is the distance from x to 0. That's a bound for all our terms xk, so long as little k is greater than or equal to big K. Now next the issue is, what about when little k is less than big K? okay, those terms could be huge. Okay, those terms could have norm trillion, quadrillion, whatever. But the key is there are only a finite number of them. So if there are infinitely many terms in the sequence, eventually they can go off to infinity. But it's going to take an infinite amount of time to get there. Okay, but a finite number of terms can never go off to infinity. There's going to be a maximum norm for all of them. Okay, so what we can do is, and I'm going to write it on this side up here, what we can do is we can let m prime be the maximum of all the norms, norm x1, norm x2, all the way up to the norm of the x big K minus 1, all the way up to that norm, and this is going to be some finite number, okay? And then we can let big M be the maximum of this finite number, which is m prime, so the maximum of all the norms of the terms of the sequence before they enter this ball of radius 1 containing the limit, and the limit, norm of the limit, which is norm x plus 1. And if we choose this big M, then we know by construction that the distance from xk to 0, which is also equal to the norm of xk, is always going to be less than or equal to big M, and this is unconditionally true for all little k. Okay, it's always going to be less than or equal to big M unconditionally. That's because if we take the terms before big K, they're all going to be less than or equal to the maximum. The norm is all going to be less than or equal to the maximum because these are all the terms before big K in the sequence. And then beyond big K, we've shown that because they eventually enter the ball of radius 1 containing the limit, their norms are all going to be bounded by 1 plus the norm of the limit. And so that's going to be our bound that shows our sequence is bounded. And if you're really loving my content, consider checking out my Patreon page. I love delivering free accessible math content, but with small contributions, I can really upscale because everything I'm doing is on my own right now. So please consider checking that out, and there are exclusive perks for you as well. And you're going to love this video. It's going to pop up on your screen right now. It's a video about how to prove the sum of the limits is the limit of the sums, which is a basic limit law using these epsilon proofs. So you're going to really practice and solidify it. Why not watch that? It's only a few more minutes, and you're really going to get a sense of that. And drop a comment down below. I love engagement on my channel, so please do so. Don't forget to leave a like and subscribe. Wish you all the best, and I'll see you soon.